Hello everyone and welcome to my channel. My name is Apostolos. I'm a mechanical engineer with a special passion for robotics and autonomous systems. In this channel, I will be sharing my knowledge, tips and tricks about robotics and engineering in general. In this first video, I will explain to you how to design and develop a fully autonomous mobile robot that can be used to transport packages in an indoor environment. This robot was the focus of my final year thesis during my bachelor's degree. I will leave a link in the description where you can find and read the full thesis in case you want to dive deeper into this project and autonomous robots in general. Before starting out, I want to mention a few things you need to know if you want to follow along with this video and build a similar robot for yourself. For all the things I'm going to mention, I will provide some great resources in the description below where you can learn more about those specific topics. First of all, you need to know at least the basics of ROS2. ROS2 stands for Robot Operating System 2 and is a popular framework used by many roboticists and it allows us to build robots faster and more efficiently thanks to the tools and conventions that it provides. Most importantly, you need to know how ROS2 works, what are workspaces, packages, nodes and launch files, as well as how to use the terminal to navigate in a Linux environment to interact with all the files needed for this project. Moreover, we are going to use Gazebo and Arvis, thus you have to be familiar with those tools. Secondly, you need to be familiar with Python, as most of the codes you will need to modify are written in this language. Additionally, some knowledge of C++ is also helpful, especially if you want to dive deeper into the different ROS2 nodes and modify them by yourself. Thirdly, you will need to use Arduino and Raspberry Pi. Knowing what they do and how they differ from each other is important. Saying that, you also need to know how to write C++ code using the Arduino IND, or at least be able to understand and modify a given code. Lastly, you will need some knowledge about basic robotics concepts, including motion, navigation, and control. For this project, I will be using ROS2 Jazzy, and all the codes will be available in the description of the video. This video will consist of 5 sections, each one focusing on a specific aspect of this project. The first part will cover mechanical design and electronics. I will show you the robot chassis, processing units, motors, and more. After that is the control of the real robot. I'm going to explain how to use Arduino, Raspberry Pi and the ROS2 Control Package to control the actual hardware. Next will be a section about SLAM. I will show you how to map an environment using simultaneous localization and mapping techniques. Next is the most exciting part, autonomous navigation. We are going to enable our robot to move autonomously from point A to point B. And before closing the video, I will show you how to download all the files and set up the system in both the simulation and the real hardware, so you can work on it by yourself. If all of this sounds interesting to you, make sure to stick until the end of the video to learn how to integrate them on a real robot and simulation as well, and how you can adapt them to your own specific platform. Also, make sure to check the description where I will leave some useful links for many things that I'm going to mention in this video. Let's start with the robot's mechanical and electrical components. First of all, the robot chassis that acts as a housing for all the components is made out of an aluminum structure, 3D printed components and a fiberglass cover. It has a simple rectangular shape with a special aluminum structure on top where you can place the packages that the robot will transport. It uses a differential drive system with one 24 DC motor on each side. The motors have integrated encoders to provide information about the rotational position of each wheel. The motor driver used for this project is the Cyber2 2X12. Additionally, a Raspberry Pi 5 with 8 GB of RAM is installed connected with an Arduino Mega. Those two components work with each other to achieve the robot's motion effectively. Two 12-volt batteries are used to power up the whole system. Some other components are used as well, such as a safety fuse, two DC-to-DC converters, an emergency button, a charging port, and a USB hub. Lastly, a SLAM-Tech Articulated A2M8 sensor is mounted on top of the robot and is used to provide a 2D representation of the area around the robot. This sensor helps the robot to perceive its environment and is needed for the localization and autonomous navigation algorithms to work effectively. Of course, if you are going to build your own robot, most probably the hardware is going to be different, but the overall architecture will be pretty much similar to mine. Now it's about time to configure the control of our real robot. In case you don't have a robot and just want to do everything in a simulation environment, feel free to skip this part. The next parts about SLAM and autonomous navigation are going to work the same way for both the simulation and the real hardware. I will explain more about them later. So, in order to control our robot, we need to be able to provide some velocity commands to the hardware and then implement a control loop system to achieve the desired rotational and translational velocity of the platform. Of course, you can write your own custom ROS2 nodes from scratch to do this, but it's much easier and simpler to use the ROS2 Control Package that provides some pre-existing common controllers that we can use. More specifically, I chose to use the default controller, which is specifically made to control differential drive robots. This is how the system works. The default controller runs on the Raspberry Pi and takes as input the desired rotational and translational velocity of our robot, which is published at a specific topic. It then applies the inverse kinematics equations for differential drive system to calculate the appropriate rotational velocity of each wheel based on some parameters that we set. Afterwards, those calculated velocities are set to the Arduino via serial communication. Then, the Arduino implements a P&D controller to calculate the control signal that will send to the mono driver in order to rotate the wheels appropriately. In order for the P&D controller to work correctly, we need a good estimation of the actual velocity of our wheels. This happens by processing the data from the two encoders as shown here. The ROS2 Control Package also handles the odometry calculations as well as the transformation between a fixed odometry frame and the rhombus base link so that we can have an initial estimation of our rhombus position into the space. Again, if you want to learn more about ROS2 control, I will leave some great resources in the description down below to check out. To recap, here is how the whole motion control system works. A velocity command is generated, either by the user manually or by the autonomous navigation algorithm. This command contains the desired translational and rotational velocity of the rhombus base. Then, this command is given to the differential drive controller that the ROS2 Control Package provides. Afterwards, the controller uses the inverse kinematics equations to calculate the rotational velocity for the left and right wheel in order to achieve the desired motion of the system. The wheel's velocities are given to the Arduino. The Arduino applies a P&D controller to calculate the control signal, and this signal is given to the mono driver and finally to the two motors. An individual control signal is generated for each motor. Finally, the transformation between a fixed odometry frame and the rhombus base link is published that provides an estimation of the rhombus position based on the actual rotational velocity of each wheel. I should note that this estimation is not very accurate as it doesn't account for possible wheel spinning, which means that over time it will drift away from the actual position. Quick note, if you find that the serial communication is not working, you may need to enable the appropriate permissions using this command. Then log out and log back in for the changes to take effect. Now that we have precise control of our rhombus movement, it's time to implement the SLAM algorithm. SLAM stands for simultaneous localization and mapping, and as the name implies, is a technique that allows us to map an unknown environment while also estimating the rhombus position inside the generated map. This technique is very popular and is used extensively by many roboticists nowadays. There are many algorithms that we can use to achieve SLAM, with the two most popular categories being the filter-based and optimization-based ones. For my project, I use the SLAM-toolbox package that implements a post-graph optimization technique for tuned LiDAR SLAM. For this package to work, we need an estimation of the rhombus position based on odometry. This is handled by the ROS2 Control Package as I mentioned earlier. We also need LiDAR data. There are many types of LiDAR sensors. The one I used is a 2D LiDAR by SlamTech that provides a 360-degree representation of the environment around my robot. SLAM-toolbox uses both LiDAR data and wheel odometry to estimate the rhombus position as it moves. It aligns each new laser scan with the existing map using scan matching. It keeps track of the rhombus path using a post graph. Over time, it detects loop closures, places where the rhombus have been before, to reduce drift and correct errors. This way, the robot builds a consistent 2D map while knowing where it is on that map. Again, check out the description if you want to learn more about the algorithm and the mathematics behind it. After we created the map of the building that our robot will operate in, it's time to enable it to move autonomously. To achieve this, I used the popular Navigation 2 framework. This framework was developed to work with ROS2 and provides many tools and algorithms that will help us to set up autonomous capabilities for our system. NAV2 breaks down the autonomous navigation mission into small tasks, and each one is handled individually by a dedicated server. First of all, autonomous navigation requires accurate localization of the robot. The NAV2 framework provides an implementation of AMCL, adaptive Monte Carlo localization, which can be used to track our rhombus position and set the map in real time. Then, we need the planner server, which is responsible to calculate the shortest path between our robot and the final goal. For this specific task, I decided to use the A-star algorithm, although there are other options that can work as well, like the Dijkstra's one. We should note that this algorithm generates a path only based on the static map that we created previously using SLAM. Dynamic obstacles are not taken into consideration at this point. Then, the controller server takes into account the global path created by the A-star algorithm and uses an MPPI controller to calculate the velocity command that the robot needs to apply for the next few seconds in order for it to follow the global path as accurately as possible, while also avoiding any dynamic obstacles that may appear in its way. The algorithm works by generating multiple possible trajectories that the robot can follow and designs them based on criteria such as global path following accuracy and obstacle avoidance. The algorithm takes into account dynamic constraints of the system as well, such as maximum acceleration. There is a great article from Automatic Addison that explains in detail how you can set up navigation to parameters effectively. Make sure to check it out if you are planning to work on a similar project. Now that we have a general understanding how an autonomous robot works, I will show you how to implement this project in both simulation and real hardware. First of all, you will need a computer that runs Ubuntu 24.04 and has ROS2 Jazzy installed. To do that, you can just follow the official ROS documentation. Now it's time to set up our workspace with all the necessary packages. Firstly, make sure you have installed the appropriate libraries needed for those packages. You will find all the commands in the description down below. Now go to my GitHub page and download all the packages as I show you here. Moreover, download the twist damper package. I am using this package to convert twist to twist damp velocity topics needed for the navigation to framework. Then create a directory for your workspace. Then create a directory called src inside this workspace and copy all the packages inside that folder. Go back, open a terminal and run the call build command to configure the workspace. For some weird reason, the navigation package launch files are not installed properly and you need to copy them manually to your shared folder as I'm showing you here. Don't forget to source the workspace every time you open a new terminal before running any commands. Now we are ready to set up a simulation for our system in Gazebo. This will enable us to verify that our algorithm works as intended before proceeding to the real-world testing. Simulation is very important in any robotics project and this allows to save time, identify errors early in the development process, and prevents potential damage to both the people and the hardware. Firstly, you need to install Gazebo Harmonic, which is the recommended Gazebo version to use with ROS2 Jazzy. To do this, just follow the instructions of their official website. If you have configured everything correctly, you will be able to start the simulation by simply running this command. This launch file will do the following. 1. Start Gazebo and load a specified word. In my case, I downloaded a simple warehouse word and I'm using that for testing my system. 2. Start the robot state publisher node. This node will broadcast the state of each link based on the robot's URTF file. Quick note here. To create the URTF of my robot, I use the SolidWorks to URTF plugin. If anyone is interested, I can create a separate video in the future to show you how to use this plugin with ROS2. 3. Spawn the robot inside the virtual environment. 4. Bridge Gazebo parameters with ROS. 5. Run the appropriate ROS2 control commands. And 6. Run the twist-mux node to enable us to use a joystick while the autonomous navigation algorithms are running in case we want to take over the control of our robot manually. If you face any errors, you may need to run this command first. By running this command once in your terminal, you will add the simulation environment to your bash script and you will not have any errors again. Make sure to replace the path with the actual path to your workspace and searching directory for your computer. Note that I'm using ROS2 Control even in the simulation. I chose to do that because I also use ROS2 Control for controlling the real robot and I wanted to make my real system as accurately as possible in simulation as well. Of course, you are now running a simulation using my robot. You can replace my URTF file with the one for your specific robot, choose a different simulation environment, and simulate your own system. Some adjustments may be needed for the differential drive controller as well, but this package can be a great starting place. In case you have a real robot, you will need to enable that instead of the simulation. For that reason, I created the ROS2 Control Package that runs on the Raspberry Pi. The Raspberry Pi runs Ubuntu 24.04 as well and has ROS2 Jazzy installed on it. It is also connected with an Arduino Mega as explained earlier. The way the system works is that the Raspberry Pi handles the robot's movement and the LiDAR data due to its low processing power, while the heavier tasks like autonomous navigation and localization are handled by the second computer. Both the Raspberry Pi and the computer are connected to the same Wi-Fi network, and the communication is handled automatically by ROS2 middleware using DTS. This allows the nodes running on both machines to exchange information without the need for manual networking setup. A single launch file is used to enable both the differential drive controller and the LiDAR node. The default launch file runs the ROS2 control node using the parameters defined in a separate YAML file, runs the Rombo state publisher node based on the Rombo's URTF file, runs the join state broadcaster, runs the Rombo control explorer node and the twist-mux node. Of course, the URTF and the parameters will be different for your robot, but the idea is pretty much the same. I will leave a great video from Articulated Robotics in the description that explains how ROS2 control works and show you how to set up your own controller. Okay, after running either the simulation launch file or the real robot control file, you can now open RVs and visualize the robot's movement and the LiDAR data. Make sure to select Autumn as the fixed frame. The robot's movement can be controlled by providing velocity commands in a specific topic. In this case, the topic is this one. Those commands can be generated automatically by the navigation algorithm, as I will show you later, or can be provided by the user using either their keyboard and the tail of twist node or a joystick. You can check out the description for more information on how to set up a joystick. For now, we can just use the tail of twist node by running this command and control our robot using the keyboard. Next, we can start the SLAM process. Run the following command, select map as a fixed frame in RVs, and just start driving your robot around. While you drive the robot around, the map of the building will be created as shown in the screen. After mapping the desired area, you can save the map using the SLAM tools provided in RVs as I'm showing you here. we can start the autonomous navigation algorithms. To do that, stop the SLAM algorithm and run the following command to enable the localization of our robot. Make sure to replace the name of the map with the one you selected previously. If you choose map as a fixed frame in Navis, you can localize your robot in real time. Lastly, run this command to enable the autonomous navigation algorithms like the controller and the planet server. You can set up your RPG window as I'm showing you here, so you can see the robot's footprint and the local and global cost map. Now use Service to choose where you want the robot to go and see it working live. And basically, that's it. I hope this video helped you get a better understanding how you can build your own autonomous robot. If you found it interesting, please give it a like and subscribe to my channel for more videos. If you have any questions or ideas for future videos, don't hesitate to leave a comment about it. Thank you and see you next time.